Okay, good morning everyone. Okay, so today we continue. Okay, until 4.2. I think the last time we stopped. Only we can. Okay, so I think I already asked you to take the notes right from the lab. Okay, so you can just see the notes, right? Okay, so we continue 4.2.3. So the last time we learned about, I think until here, because I write something here. Wait, yeah, this one I already. If I write something, means I we already done about that one. Okay. Mm, yeah. Mm-hmm. Yeah. So until this part, so maybe we already finished this one. Okay, so we're gonna continue. We determine the direction, right, of induced current, okay, in a straight wire, okay, on or a solenoid, right. So determine the direction of induced current. So I already like mark like half of your exam paper. Yeah, when I think there's one question that asks about the rule, right? What type of rule that you need to know, you need to use, okay, for to find the direction, okay? So some of you said Fleming's right hand rule, right? So you have to remember for the right hand rule is actually for induced current. Okay, so means in this current, whenever you see there is no battery, right? So there is no battery, there's only a galvanometer, okay, and there's a, let's say, the in conductor, right, cutting the magnetic fields, okay, and they're using the galvanometer. They mentioned about the induced current, or in the diagram they didn't show the battery, the cell. So means that one you have to use hand rule, okay, Fleming right hand rule. But let's say in the diagram in the exam, I think they put the battery there, right? You need to find the direction. Okay, they put the battery there, so the right cell. So it's supposed to be Fleming left hand rule. Okay, so you need to know the difference. Okay, Fleming right hand rule, Fleming left hand rule, when to use it. Okay, another one we learn about Lenz's law. Okay, all right, so this is the activity. Okay, so to indicate the direction, so we already know the induced current is produced, right, when we cut off the magnetic fields. Okay, we have the conductor here. So let's say this is the magnetic fields. Okay, and there is a conductor here, and you cut the magnetic fields. It has to be perpendicular. Okay, it has to cut it has to cut the magnetic field so it can produce the induced current. Okay, so that's the rule, and there must be a motion. Okay, motion is whether the magnet move or the conductor move, right? But there's need to be a motion. Okay, so this is the Fleming right hand rule. It's just same as the Fleming left hand rule. It's just that you use your right hand. Okay, so this is the force, right? The thumb is showing the force here, and this is the north, and also this is the south. Okay, and this is the direction of the current, right? So this is the direction of the current. Okay, and then wait, I change the USB. Okay, then another part is okay. So to indicate the direction of the induced current in the straight wire. Okay, so how you want to find the direction of the induced current? Okay, before this, if in the the electromagnetic, the one that we learned before, that using the battery, okay, and then you can cut off, we can produce catapult field, all that, right? So that one they have you use a battery, so you know which way that the current will move. It should be positive to the negative, right? So we already know where's the direction of the currents, because they have the positive and the negative terminal. But in this one, there is no battery, right? So how do we know that which direction, I mean, which the direction the current will flow? Okay, whether clockwise or anti-clockwise, right? Okay, so we have to use the Fleming right hand rule. Okay, so we have to use the Fleming right hand rule. Okay, so the first one, okay, moving the wire upwards. Okay, so now we have the movement. We know the movement, right? We know the force. Okay, I mean the movement here, you move the wire upwards. Okay, so in the before that we learn before this one we have to find the force, right? Which way does the copper rod will move? Okay, but this one you already have the direction because you are the one who make the motion, whether it should be up and down, all right? Okay, so the first one is moving wire upwards. Okay, so upwards means the force should be going upward. Your thumb should be going upward like this. Okay, and then you already know the pole, right, for the magnet, north and south. So north and south here. Okay, and there's a direction of current means it goes at this way, right? So mean if we go at this way, okay, so you have to see the third fingers here, right? So it goes at this way. Okay, then after that we just complete the circuit here, and you can see the arrow of the galvanometer will follow the direction of the induced current like that. Okay, so it will follow like that. Okay, but actually in the textbook, right, if you notice, okay, it's different because actually direction of the current is the flow of the electron, right? So the flow of the electron that produce the current. So usually if the direction of they will be opposite. Okay, it will be opposite. So let's say the direction of the current is flows from here. So means in the direction of the electron is actually is opposite of it. Okay, so moving wire upwards, it should be P to Q. Okay, correct, right? This one I already show you how you get the current goes from here to here. The moving the wire downwards, so it will be in the opposite way, same as just the one that you answer in the exam, right? They say what happened if you change the pole, if I'm not mistaken, or what happened we change the terminal of the battery, so it will just change the direction, okay, in the opposite direction. Okay, it will still move because some of you say it's not moving, it still move. Okay, the copper rod will still move even you change the pole of the magnet or you change the pole of the battery, it will still move but in the opposite direction. Okay, or you can say it changed direction. Okay, so for this one, underline the correct answer. So moving wire upwards. So this is for this one actually. Okay, so moving the current upwards. Alright, so same Q to P. Okay, and then moving the wire downward. Okay, so it will go from P to Q. Okay, so this is for this one. For number 3, this is for number 2. Okay, for number 4, it asks you to determine the poles at P and Q. Okay, so now the direction of the movement is going upward. So your thumb going upward. Okay, and then the poles. Okay, so now we don't know the poles, right? Which way does it move? Okay, sorry, which one is north, which one is south. But they give you the direction of the current. Okay, so means it should be like this, right? Going at this way. Okay, so you can see here, right, the direction of the current, you just complete it, right? The direction of movement is going upward. Okay, so this is your south, right? This one is not, right? This is south. So south and north. Okay, so you need to complete the circuit. Okay, so sometimes can ask you to find the poles of them, or maybe they ask you to find the direction of the current, right? So maybe they ask you which way does it move, okay, direction of movement, okay. So it depends, okay. But this is you use the right, and of course you need to know this one have to use the right hand, no left hand, right? Because I noticed a lot of you put it as a Fleming right hand rule. Okay, actually right is only for induced current, no battery. You have to see the diagram. Okay. Alright, so indicate the direction of the induced current in the solenoid by Lenz's law. Okay, so what does Lenz's law say? So the induced current always flow in the direction that oppose the change of magnetic flux that cause it. Okay, so it will always oppose. Okay, so let's say it's just like never mind lah, I just give you a simple one. Okay, so let's say this the magnet come towards the solenoid. Okay, so and then after that what the solenoid will do, it will oppose it. Okay, so when it become want to be towards the it move towards the solenoid, so the solenoid will try to push it away. Okay, so when you try to push it away, so this one, okay, you have to put the same pole, right? Because same pole will oppose each other. So this one should be put north, okay, north, and this one should be south. Okay, so they will oppose each other. So that's what Lenz's law said. Okay, so the induced current that will flow will oppose the change of magnetic flux. So means if the magnet come near to the solenoid will try to push it. Okay, and you can use, so how we know, right, which way does the direction of the current will go? Okay, so use the right hand grip rule. Okay, so this is the knot, so it should be the thumb here. Okay, your thumb should be the knot side. Okay, and the south is on the back there. Okay, so the knot is on your thumb, so you can see your four fingers will show the direction. So if like moving upward, okay, it's like this. Okay, using the right hand grip rule, not the Fleming left hand rule or right. Okay, so you can just like hold the solenoid. Okay, and your thumb should be on the knot side, and you can see the four fingers, right, we go upward. Okay, then you just uh complete the circuit like that. Yeah, like that. Okay, so this one they say it move towards. So what happen if it move away from the solenoid? So when it move away, the solenoid will try to attract it. Okay, because it oppose. Okay, so when this magnet try to move away from the solenoid will try to attract it. Okay, so in order to make it nearer, make it closer to the solenoid, it has to be the different pole, right? So this is south, so this one should be north. Okay, and this one should be south, because different pole attract each other, right? So this is, and then again you can use the right hand grip rule, okay, to find the direction of the current here. Okay, so that is the Lenz's law said. Okay, so kalau macam dalam bahasa Melayu lah, I don't know like what they call it in English. So kalau orang Melayu dia kata hukum macam jual mahal. You know, like jual mahal. Okay, like I say you like one girl, right? Okay, and then you try to approach her. Okay, but then like she rejected you, but actually inside, okay, she wants you. Okay, then when you be rejected, of course you will like make a distance from the girl. Okay, go away from the girl, but then the girl like try to attract you back. Yeah, so kalau dalam orang Melayu lah, kalau bahasa Melayu kita panggil hukum jual mahal. I don't know whether you can understand, but I just like you can use that concept here. Okay, it's just like macam katalah magnet ni datang dekat kan. So let's say the magnet represent the boy lah. Okay, so the boy come to approach the girl here, the solenoid. Then of course lah jual mahal kan. Jual mahal maksudnya you tak nak kan. So you jual mahal tak nak. So you of course akan push dia away. And so you have to put a same pole here, right? So it will move away. Okay. Then okay lah, fine lah. You dah tak nak saya. Okay, you don't want me. Then I will go away. Then okay, then the magnet move away. Okay, then the girl like no. Okay, actually like try to attract that one, try to attract back. Okay, try to attract you back. So that's the concept if you want to, like make it easy to understand, or it depends on you. You can just remember like this also can. Okay. All right. So that's the Lenz's law. Okay. Okay. So for this one, right. How do we know the wait? When current flows in the solenoid, okay, magnetic field is produced around it. Okay, so you already know when the current flows, right? When its current go into the paper, right? Go into the paper, it will move clockwise, right? If move out from the paper, it will go anti-clockwise. Okay, so means the current also has a magnetic field. So the current flows from positive to negative terminal. So this one we already know, right? From positive to negative. Okay. Okay, so the solenoid becomes magnet. So you can use the right hand grip rule. Yeah, so this is the one that I said just now. Okay, right hand grip rule. So your thumb showing the not one. Okay, so how do we know this is not, or this is out, or this is out, this is not, or this is out? Okay, you can see the line here. Okay, the what I mean the direction here, right? This one for the solenoid, it move downward, right? So your four fingers, okay, we produce the direction. Okay, we represent the direction. So the direction going downward. So this one also going downward. And right, you can see your thumb showing to the right. So mean the right is your north and this one is your south. Okay, so this one going downward. Okay, so your four fingers also should move downward like that. Okay, and the knot, okay, the thumb will show the north side. So this is the north and this is the south. So you can use this one to find the pole for the let's say for the one that will electromagnetic induction also you can use this one. Okay, just to find the poles, because some of I know that the method they use, that looking from at this side clockwise, looking at that side anti-clockwise, so it's quite hard for you to like to imagine. So for this one you just use the right hand grip rule. Okay, so four fingers going downward, so your thumb going to the right, so means your right is the north. So just remember, thumb represent the north side. Okay.
By this way, it's
Okay.
given by what we know as
So
Lenz's law. Let
let's
us
law.
understand this law in details. When a magnet moves with its magnetic field near a coil,
Okay.
towards or away from it,
Okay, so when you move towards or away from it, of course, the magnetic lines will be cut off. So mean that will produce the induced current. Okay, means every time the magnetic field being cut off by the conductor, of course, they will produce the current. Okay, so it's up whether it induced current or another one that we learn. Okay, so for just remember, if they put the galvanometer no battery, that one of course induced current. But they say they have a battery there, no, that's not induced current, so you have to use your left hand. Right. Okay, so you can see it cut off the magnetic field, so it produced
this
the,
produces an induced current in
yeah,
a
induced
certain
current.
direction.
Right.
According to what we had before in the electric motor, every current makes its own magnetic field.
Okay. So remember when it come closer just now, right? Okay. So this is the direction. How do we know the direction of this one? Because I just tell you just now, right? When it come closer, this one will push it away. So this one and this should be a north and this should be a south. Then it will change the direction. Once it move away, right? This one, the pole will change because it will try to attract back. Right? The same I said, I cakap tadi lah macam jual mahal tadi kan. Okay, so it will change the directions. Okay.
So the produced current in turns will create its magnetic field around the coil. It's clear now that we have two magnetic fields. The magnetic field of the magnet that causes the current, and the magnetic field around the coil that is caused by the current. Lenz's
Mm.
law tells us that the magnetic field caused by the induced current will oppose the effect of the magnetic field of the magnet that causes the current.
Okay. So when it moves here, right? So if we move towards it, this is north, this is south. So of course there will be a current flows, right? Because the magnetic fields here being cut off. Okay. So this one will become, there will have the induced current that flows. Okay. Then they will oppose. Okay, it will oppose the effect. So the magnetic field caused by the induced current. So where does the magnetic field this one come from? It come from the induced current just now. Okay, and it actually it's actually oppose the effect, the magnetic field causing the induced current. So mean it oppose like this one I said. Okay, when you try to move away, to try to move closer, it will push you away. Just like that. So you have to know the pole. Okay, and you can find the direction by using the right hand grid rule we just learned just now. Okay, but the important thing, remember your thumb is actually usually represent north. Okay, north side. Okay, the next one. Indicate the direction of the induced current in the solenoid. Okay, so magnet is moved towards the solenoid. Okay, so when it move towards, okay, I just discussed just now, it will repel, right? So it have to be the same pole. Okay, and of course you can use the right hand grip rule. Okay, right hand grip rule. Okay, but then this is the, you can see the directions, right? The direction is the opposite way. Okay, because this is actually the flows of electron. So the direction before this, in before the new syllabus, your KSSM, right? The KBSM one is actually the current we follow the the flow, the current, the induced current we follow the direction of the induced, the induced current. Okay, but they, you know, like they make it new. Okay, actually, right, even that the current is like, you know, is flowing at this way, okay, on to the right, but the current we go to the left. Okay, the governor meter we show to the left, right? Because, okay, wait, I explain to you. Okay, this is a positive and negative terminal, right? Okay, so we know that the current flows from positive to the negative, correct? Okay, but we know also that a current is actually the electron flows, right? So electron means, of course, the part that have the most electron is on the negative terminal, right? So that's why if the electron flow, we flow at this part. Okay, so when it flow at this part, so this positive is actually that we have more electron. Okay, because the electron move at this way. Okay, so this one at this part, then we have more electron. So more electron, then the current will flow at this way. Okay, so you just need to remember, okay, even the direction of the current is going to the right. Okay, but the direction of the galvanometer we go to the left. Okay, because the flow of electron is actually opposite way, right? Even like in positive negative is like this, but the current is follow actually positive, the current flow like this, right? Whenever you label the diagram, okay, in the electricity chapter, right? But then actually the current is a meaning is actually the electron flows, right? Flows of electrons. So negative should be like this. So that's why it actually opposite. Okay. So mean this one shows the flow of electron. But actually for positive negative side, it will go at this side. Right? So what is produced on the solenoid if current flows through it? So the solenoid become electromagnet. So mean it will attract. But electromagnet is a temporary only. Okay. So it's only like if there is no motion, right? There is no motion between the magnet or the solenoid, then means there's no induced current, then the solenoid will lose the electromagnet. Okay. So electromagnet is only temporary. Okay. So this next one, push the magnet towards solenoid, we produce induced current. From Lenz's law, what will the solenoid do in order to oppose the motion that produce the current? So the answer is must push out the magnet. So it have to repel it. So in order to repel it, it has to be have the same pole, right? So that's the Lenz's law said. It will oppose. Okay, the next part is to indicate the direction of the induced current. Alright, so this one also we already discussed, right? How to find whether which part is north, which part is south. You just see this direction, right? So it goes downward. So your right hand, four fingers, okay, going downward, okay, and your thumb will show the north side. So your north is actually on your right. Okay, so this one should be on your south. Okay, but sometimes they give you this one. Okay, they give you this one. Okay, they give you north and south. Okay, but then they ask you what pole is this one? What pole that should be used at this part? So you need to know if this one not right and it come closer means this one should be not to, because it has to repel, right? And sometimes the question also asks the direction of the magnet. So you need to understand well about the Lenz's law. It has to oppose. Whatever it has to oppose. If they say someone come to near to you, you will try to push it away. Or let's say someone, like, okay, make a distance from you. So you want to attract, attract it back. So it's same like that, the concept. Okay. Alright. So this one is actually for, remember the 4 marks question that you need to explain. For the exam, I think 4 mark is the first one. They ask you about the impulsive force, right? Yeah, you need to explain why you need to take, like make like length the time of the impulsive force, put it backward from of the bed, right? That one, the first question. I think the second one is the refraction, right? How does the refraction occur? 4 marks. So this is actually for you to help answer for 4 marks questions. Okay. So I just give you the translation. Okay. So this says the north pole. Okay. Will come towards the solenoid, right? And the solenoid will become electromagnet. Okay. So then the direction of the induced current will be produced at the north, okay, in the end of the solenoid, so it can follow the Lenz's law, right? So Lenz's law said it will oppose. Okay, so this is the direction, right? But then you have to see the direction of the galvanometer is opposite, right? So remember that one. Okay, so I will not discuss this one. This one is the same. Okay. Yeah, this one also same, but this one change because the knot become here, become at on the left because of the direction here. See, it moved upward. Now your fingers move upward. Your 4 fingers move upward. So your thumb will show at the left side. So means your left side is your knot. Okay. So use the right hand grip rule to find the pole. Then you can use the right hand grip also to find the direction of the magnetic field, right? Whether it move clockwise or anti-clockwise. But then it also can be used to determine the pole of the magnet, right? Okay, so I will not discuss this one. This one also same. This is like repeat it again. Okay, so this one I think you can see, sorry, you can see in the textbook, right? What happened. So you can see the direction of the galvanometer, right? We already always like oppose, right? You see it flows to the right, then it goes to the left. Okay. But remember for the galvanometer, the zero, like zero, the starting point zero for the reading is on the middle. It's not same as the ammeter or the voltmeter. Ammeter and voltmeter is at the end, right? Zero and then 1, 2, 3, 4, 5 like that. But for the galvanometer is on the center. The zero is at the center. So whether it can so that's why it can move to the right or to the left. Okay, because the zero is at the center here.
In the first
Okay, so I will not discuss this one. This one also same actually. It just like revision like that. Okay, what causes the currents to produce in the conductor? So the magnet move into the solenoid and there will be cutting of magnetic flux. So if they say you don't use a magnetic flux, you can say magnetic fields. It's actually the same. Okay, magnetic flux or magnetic field is actually the same. Okay, so you can say if magnet move into the solenoid, then there will be a cutting of the magnetic fields. Okay, so as the name induced current names the law used to determine the direction of the current. We use the Lenz's law, right? So in order, like we know this one, let's say this is move away, right? Okay, then it have to what? It has to attract it back. Okay, the solenoid have to attract it. So this one should be south. Alright, then this one south, this one also should be north. Okay, then after we know this one is north, this one is south, you can use your right hand grip rule to find the direction of the current, right? So your thumb is showing north, right? And then you can see your four fingers going downward. Okay, your four fingers going downwards, but this one it has some arrow. It should be this way because it's already always opposed, right? Okay, so explain factors that affect the magnitude of induced current. Alright, so this one we use a Faraday's law. Okay, so you need to know the difference. Lenz's law, what is the Lenz's law? Lenz's law is actually is a magnetic the induced current will always say or direction of the induced current will always oppose, the change of the magnetic flux. Alright, that is a Lenz's law. We used to determine north south, the right direction of the current. But what is the Faraday's law? Faraday's law states that magnitude of the induced EMF or induced current is directly proportional to the rate of the cutting of magnetic flux. What does it mean? It means the more lines, the more of the magnetic field, the lines of magnetic field you cut means it will produce more induced current. Okay, so let's say if I have this is the magnet, right? Okay, not south. Okay, it should be goes from here to here. So, and I have another magnet. So let's say this one, the magnet is much stronger. So when you say the magnet much stronger means the magnetic field line is more than the upper one, right? Wait, okay. So, right? Oh wait. Okay, then it says here, right? Thus, the magnitude of the induced EMF is directly proportional to the rate of cutting of magnetic flux. So, mean if they cut more magnetic fields or magnetic flux, right? So, the induced current also will be increased. Okay, the value of it will be increased. The magnitude of it will be increased. Okay. So, for the relative motion of the straight wire and magnet, the induced EMF increase when the speed, right? Means you move it faster. Okay, upward, downward faster. It has to be perpendicular, right? Okay, it have to be moved upward and downward. Okay, very fast. Then you can have the induced EMF. Okay, you have the induced EMF will increase. Or you use the strength, you increase the strength of the magnetic field, like the one that I give just now. Okay, so compare these two diagrams. This one have more magnetic fields, means it's much stronger. So that means we cut more. This one we only cut two, right? Two magnetic field. This one we cut four. So of course this one will produce the higher induced current. Okay, all right. So for this one is for straight wire, means only one wire. Okay, like that. And not south. Okay. And then this is a wire, a conductor here. Then we connected it to the galvanometer. Yeah. So this is for this one, right? That's why I said straight wire here. Okay, but for the solenoid is which one? The wire that we, make it as a coil, right, around the conductor. Okay, so they produce a solenoid. So solenoid and magnet, it will increase the induced EMF if the speed. So this one is the same. Okay, you cut it off, you increase the speed. It will produce the higher induced current. Okay, or you increase the number of turns. Okay, so mean you increase the number of turn the coil here, right? So let's say the example is like this. Okay, I have a solenoid here. Okay, so this is only like the number of turn is 3. Okay, but then another one I put it like that. So which one have the higher number of turns? Okay, so of course this one. So this one will produce the higher induced current. Okay, and last one, the strength. So this one also same as the straight wire. If you use a stronger magnet, of course, okay, of course you produce the induced current, okay, the induced current will be higher. So this is actually the one that we just, to prove, right, whatever the factor that we said just now is correct. Okay, so speed movement, if you like speed of movement A, it says here the movement is the magnet is moved slowly. So mean, of course, small deflection, small current, it move faster. Big deflection mean, I don't suggest you use the word big, because big is actually usually for size. So you use high deflection or more deflection, okay, higher deflection, right, like that. So big current, big is actually for the size of balloon, let's say. Okay, number of turn, small deflection, small current. Okay, if the solenoid, you increase the number of turn, it have to be big deflection, no, high deflection and high currents. And if you use the strength of magnet, right, if they move, the strength of magnet is on this one, you use only one magnet, this one is 3 bar magnet, so mean more magnetic lines there, right? So of course you have to be big deflection. Okay, so this is the 3 factors. um okay, this is only the example. Okay. So design a direct current and alternating current generator. Okay. So before this, we learn about the direct current, right? We use a commutator, if I'm not mistaken, right? So what is the function of the current generator? Okay. So it's actually, let's say you go to the night market, okay, pasar malam kan? Okay. There's a one, like uh, the noisy one, the machine noisy one, and of course you wonder how they get the electricity kan. Takkan lah ada plug kan, switch kat dekat merata-rata tu kan, nak pakai extension ke apa kan. So of course there be some machine that can produce the electricity there. So that we call as a generator. Okay, yang bunyi bising, bunyi mesin tu kan. Then jadi kalau you pergi nak market, then of course they will have that one. Okay, because they need to have that. Okay, to produce a current. Okay, so direct current generator. What is the function of the current generator? So it's actually a device to convert the mechanical or kinetic energy. Kinetic energy means what? Kinetic energy is any object that moves. We have the kinetic energy. So what is meaning of the kinetic energy? The energy that cause the movement or the object move. Okay, so that's the meaning of the kinetic energy. So kinetic energy to the electrical energy. So state the physics concept involved in the working principle of the current generator. So we call it as the electromagnetic induction because we use the induced current. Okay, and we use a magnet to produce the electric. Okay, so we use the induced current, okay, and also we use a magnet to produce the induced current and it produce the electricity. Okay, so electromagnetic induction. So this one you have to know physics concept, laws, okay, or what rule. So it has to be precise. You cannot simply put, let's say they ask you about the one Hooke's law, right? Okay, some of you say Fleming left a Fleming left hand rule. Okay, but they ask you about the law. You answer its rule. So no, they have to be same. If they ask you about the physics concept, okay, means the concept you use is induction, right? Induction, induced current. Okay, but they ask you about the law, Hooke's law. If they ask you about the rule, okay, what rule that you use, okay, so that means to be Fleming left or Fleming right hand rule. Or they ask you about the laws, there is a Lenz's law, Faraday's law. So that one you cannot change. That's the reason why they call law, why the reason they call rule. Okay, now what is the concept, right? So you need to be have to know the difference. Okay, so name two type of the current generator. So we have two type of current, right? The first one is a direct current, DC. Okay, usually in battery you use the direct current, that one. Okay, but this one we use the concept to produce the DC current. We are not using the battery here. Okay, so we only using the coil, all right, and then the of course the magnet. Okay, then it move, it produce the direct current. And another one is the alternate current generator, or we call it as the AC generator. Okay, alternating current. Okay, so there are two types of the current generator, same as the one you learned before, AC and DC. Okay, but this one they didn't use the battery or power supply. Okay, they use a magnet and they use a coil there, and you move it, and also they have a commutator or the slip disc, slip ring, sorry, slip disc, slip ring. Okay, to produce the induced current. All right. So let's see the first one. All right. This is a diagram. Okay. Usually, what they will ask you, okay, is the difference, right? What is the part that has the part that can differentiate the direct current generator and also AC generator? So the part that actually difference between those two diagrams is actually this one, right? Commutator. Okay, and another one is slip ring, right? For the AC they use a slip ring. For DC they use a commutator, right? Okay, so this is the coil, and this is, of course, we use a magnet, all right, and this is a commutator, and this is a carbon brush. So the carbon brush need to be touched with the commutator in order for the current, for the induced current to move. Okay, so whenever you want to, let's say the question come out, ask you to discuss. Is it question 4 marks? Discuss about the induced current. Make sure you put induced current. Don't put current. Current and induced current is a very different thing. Current is actually produced by the dry cell or by the power supply, right? But for the induced current, it's produced by the magnet and also by the movement. Okay, so you need to know the differentiation. Okay, so this is the diagram. Okay, the light bulb is actually to prove that there is a current flow, of course. Okay, and this is the carbon brushes, and this is the permanent magnet. All right, this is actually for um okay, you can see the diagram there. Oops. Okay. Okay, explain how the current generator produce the current. So you see the diagram here. You use a commutator, right? So you already know this is a DC current. Okay. So how to explain? How to explain? This one can come out for 4 marks, right? 4 marks questions. So the coil is rotated in clockwise direction. Okay, so of course this one, right, it will move. Okay, so it will rotate. Okay, it will rotate. Okay, and when it rotate, it will produce what? It will produce the magnetic fields lines. Okay, it will they will cut the magnetic field lines. So when they cut the magnetic field lines, what will be produced? Induced current will be produced. Okay. Okay, so right. I just, like, oh wait, okay. So how about the directions? So remember this one. This is just same as the Fleming left hand rule, right? Remember I teach you in the class, right? To find how to find the direction when the current goes. This one, they give you the current, of course lah, the direction of the current. But they see the one that we learn, they give you a battery. Of course, you know lah which way that it will move, right? Okay. So this one also same, but you just use your right hand. Okay. So north south, FIB ni, FBI is actually force, B is actually magnetic field. It's actually symbol for the magnetic fields in the physics term, right? And I, of course lah, is the current, right? Okay. And then here it says the coil rotate in the clockwise direction. Okay, so how do we know clockwise? Alright, so you know that the current flows at this way. Okay, the current flow at this way. Okay, and the force going up. Okay, and the north, this is north, right? North and south. So north and south. Okay, so at this part AB, it will move upward. Okay, at the part CD here, okay, now is different because the current is going out from the paper. Okay, so when it goes out, okay, the force will go down, right? And same the magnetic fields, north and south, north and south. Okay, and then the current, it goes this way. Okay, so it's actually the picture, right? Yeah, because cannot show in 3D, right? Okay, so it will move this way. Alright, so now this one move upward. Sorry, downward. So what happened here if we rotate like this? Okay, this one going upward. Okay, then it go this way. Okay, then this one go this way. Okay, if we rotate, so AB we go to CD, right? And CD we go to AB. Okay, if we change, right? Okay, so the coil rotate in the clockwise direction. So it move like this. So it's a clockwise. Okay, and you use the Fleming right hand rule. So the current will flows from ABCD. Okay, so you need to know this one. The current can be determined by the movement and also by the pole of the magnet. Okay, which way that the coil move. If you move upward, mean your force. You mean your thumb have to be upward, right? And then your knots out. You already know lah. Your fingers right here is not, and here is out. Remember that one. Okay, so in the horizontal, okay, this one just discussed just now. Okay, what happened when the coil, the coil is like this. Yeah. Uh, right? So what happened? That one, there is no magnetic field be cut at that point, right? Because there's no, the magnetic line can flow through the coil there. Okay, so there will be no magnetic fields be cut. So how does it move? Okay, so it move because of the inertia. Okay, this one also will come out. I mean, like, I'm not sure it will come up, but let's say the question come out why it can move, right? So it's actually because of the inertia of the coil there. Okay, it still insists to move, right? So remember what is inertia? The tendency of an object, right, to move in the straight line or move in the if move in to move a straight line or stationary. Okay, unless there is a force acted on it, right? Okay, so that one, so the direction, so direction of induced current, you can determine by using the Fleming right hand rule. Okay, we know the direction where it move. Okay, it move upward. Okay, so your thumb going upward. Okay, and then your north south. So north south. Then you can see your third fingers show which way. So that is the direction of the induced current. Okay, so it will move this way. Okay, but again, okay, for the galvanometer, it will move at opposite way. Okay. So this one I already discussed. Okay. So bulb lights off. Okay, but at this part, no current will be produced. But it will still move because of the inertia. Right? There is no induced current, but it will still move because of the inertia. Okay, so bulb lights off, no deflection. So when it called at the vertical position, sides A, B, C, D parallel with the magnetic fields. Okay, so it just can pass through like that. So there is no cutting of magnetic fields and no induced current. Okay, so means at this part no induced current, but what make it move because of the inertia. Okay, this one, they change the side, you can see, right? Because they rotate, right? So when they rotate, the AB here, we go at CD here, and the CD here, we go here. Okay? So again, we use the Fleming right hand rule to find the direction of the current. Okay? So your AB, we go downward, your CD, we go upward. So state the direction, right? And what is the direction? This one, use the Fleming right hand rule. Okay? Then remember lah, of course, right? See the direction of the current to the left, but the galvanometer moves to the right. Okay, so that one is the first half cycle. So first half cycle means the current from AB flows through CD. Okay, and then the galvanometer moves to the right. Okay, and then for the second half cycle means it moves from here to here, B to A. Okay, B to A, and then D to C, right? Just now A to B, C to D. Okay, when it change the positions, right, turn, okay, then the current move at B to A, okay, and D to C, B to A, D to C, like that. Okay, just now like this, and then when it change, it come like that, right? Okay, so the commutator, what is the purpose of the commutator? Is reverse the direction of the current in the coil for ever half rotation. So the commutator, right, it changed the direction, it reverse the direction of the current in the coil. So that's the function of the commutator. Okay. So purpose, the direction of the current in the output circuit or galvanometer always same, okay, from Q to P. This is for the second half lah. Okay, this is first half. Okay, then we come here, it becomes second half. Okay. Mm-hmm. Okay, so this is actually the, how does the DC generator, okay, the movement like that. So only one way, okay. All right, now uh, this one, okay. So this is the diagram, right? I just show you the line, right? Okay, so here starting from this point, okay, when it a bit when it a vertical, okay, vertical to the coil is vertical, so you already know no induced current, so that's why zero here. Okay, but then when it's same in this kind of arrangement, right, so there will be the induced current, so that's why you have induced current here. But then again it turn around, then it have to be like this, right, vertical, so it has to be zero because no induced current produced, no magnetic field being cut off. Okay, then here again, right, horizontal, then means there is a cutting of the magnetic fields, so there will be a current. Okay, and then this one, no current. So this is what can you say about the magnitude and the direction. So the induced current is zero when the coil is at the vertical position. Okay, so this is the proof that when it's a vertical position, the induced current is zero because there is no current produced and the bulb is not light on. Okay, and magnetic fields and movement to the coil is parallel, no cutting or magnetic bulb. So the induced current is maximal when the coil is at the horizontal position. So means at the horizontal like this, okay, the horizontal means it has the induced current, so that's why it shows the maximum, right? So this is actually the angle, okay, the angle. So this one is zero, and when come here 90 degrees, okay, and then after that become 180, then 270 and 360, okay, complete circle. So what is the name of the current here? Here we call it as the direct current because it's only move like one way. Okay, what is the name? Because only one way. If at AC current, then that one they have to be low part here. Okay, because they will change the direction. Okay, we will see that one later. Okay, so I think I will stop until now. Okay, so we continue on tomorrow. I think same time. We continue with alternating current, then we go to 4.3. Okay, so if I already finish the finish marking, I will put the mark in the group. Okay, so I see you tomorrow. Okay, thank you class for come to my class today and sorry, okay, for everything. Okay, and thank you. So if they say your friend cannot come, you can, I will put this video on the YouTube. Okay, so you have any question, you can just PM me, right? Thank you. Bye. Welcome. Bye.